Welcome back. In this video, I'm going to explain diagrams and graphs. Let's consider this table pertaining to fruits production in 2005-6. The data is in million tons. I have taken here 4 districts: Chikmagalur, Chitradurga, Kodagu, Shivamoga. In these 4 districts, fruit production like mango, papaya, orange, banana, these fruits in different places, around 58,000 million tons in Chikmagalur mango production, and papaya production in Chikmagalur 9,300 million tons. Like this, in Chitradurga, mango production is 34,000 million tons. In Shivamoga, 32,500 million tons. This whole thing represents the fruit production in 4 districts. The table generally do not make the whole thing clear at a single glance. So which place having highest fruit production with respect to particular? So at a glance, we may not get the information. If they are presented in some kinds of diagrams and graphs, it will be helpful in understanding the information easily. So here we can use diagrams and graphs to represent the data. Mainly the difference between diagrams and graphs. So diagrams are suitable to represent the data relating to different attributes or variables. But graphs are more suitable to represent continuous frequency distribution and time series data. These graphs are not suitable for attributes. And with respect to diagrams, these diagrams do not represent the mathematical relationship, but graphs represent mathematical relationship because it uses time series or continuous frequency distribution to represent the data. The diagrams and graphs are tools of presentation. First, I will consider diagrams, types of diagrams. There are 2 types broadly: one-dimensional diagram and two-dimensional diagrams. One-dimensional means only length is used to represent the volume of the characteristics, but two-dimensional means both length and width are used to represent the volume of the characteristics. For one-dimensional diagrams, examples are simple bar diagram, multiple bar diagram, subdivided bar diagram, percentage bar diagram. For two-dimensional diagrams, example is pie diagram. Let's consider the only mango production. Okay, this is in million ton in different places, districts, 4 districts. This is the mango production data in 2005-6. We can represent this table or data in this way. So this is Chikmagalur and Chitradurga, Kodagu, Shivamoga. For these attributes, with Chikmagalur, how much mango production is 58,000, Chitradurga 34,000, Kodagu 3,000, Shivamoga 32,500. So in this way, we can represent the data. This is known as simple bar diagram. So here in this diagram, this is x-axis, we have taken the different places. This is y-axis, we have taken the production, only production here, and this is here in x-axis places. The whole thing represents mango production in 2005-6. This simple bar diagram, it is used to compare the volume of the single characteristic between different attributes. Here attributes are Chikmagalur, Chitradurga, Kodagu, Shivamoga. These are attributes. We are comparing this mango production with respect to different places. In this situation, we can use simple bar diagram. So compared to previous table, here I have taken the papaya production with the addition information. So in this situation, to represent this type of data, instead of simple bar diagram, we can use this type of. With this each attribute, another one more bar, one more column. So we can observe here, This first column indicates mango production with respect to Chikmagalur, around 58,000. And this is another column is papaya production 9,300. So to differentiate papaya and mango, we can use this legend. We can use this legend. So blue indicates mango and gray color indicates papaya in all the districts, in all the places. So here this is production, this is the places. This type of diagram is known as multiple bar diagram. Generally, multiple bar diagram or compound bar diagram. So this diagram we can use to compare the volume of two or three interrelated characteristics within different attributes. So within different attributes, different places, two or three characters. Here only two characteristics. Mango is one character, papaya is another characteristic. These are the volume or value with respect to production. For comparing two characteristics, particularly we can say double bar diagram. Actually, this is the double bar diagram. Only two bars under each attribute. Two bars on each attribute. This is particularly known as double bar diagram. For comparing three characteristics, we can say triple bar diagram. In triple bar diagram, under here in Chikmagalur, one more column, one more bar will be there. In that case, that's triple bar diagram. For comparing more than three characteristics, multiple bar diagram, we can say. Multiple bar diagram. This is generally multiple bar diagram. I've taken another one more example. So compared to previous table, I've taken orange production and banana production with addition. In this situation, we can use this type of bar diagram. So here we can observe under Chikmagalur district. So this portion indicates 58,000. Another this color brown color indicates papaya production under Chikmagalur around 9,300. So next is this light brown color. This indicates orange 7,000 million tons, and this purple indicates 85,000 million tons banana production. So under each attributes we can observe like this. This is the legend. To differentiate the characteristics within the attribute we can use this is a legend. This type of diagram is known as subdivided bar diagram. Under each bar is subdivided. That's why it is subdivided bar diagram or component bar diagram. This diagram is used to compare the volume of multi-character data within different attributes. So multi-character, mango, papaya, orange, banana. The multi-character data. Have taken this same table, previous table, which I have used for subdivided bar diagram. I have taken same table. This table can also represent in this way. So under each attribute, the same portion. So here, using this percentage formula, we can use this type of diagram. Under each value 58,000 we can convert to percentage. 9,300 can be converted to percentage. Each volume can be converted to percentage. See, we can observe in this table Chikmagalur. So total 58,000. This is a percentage is equal to component value divided by total of component values into 100. Component value here is 58,000. Total of component values means 58,000 plus 9,300 plus 7,000 plus 85,000. So total 1,59,300. So this can be multiplied with 100. This becomes 36%. In this way, second papaya 9,300 divided by 1,59,300 into 100. This becomes 6%. Like this, all the values can be converted to percentage. This percentage can be represented like this in this bar diagram. This type of diagram is known as percentage bar diagram. To compare the volume of multi-character data within different attributes, we can use percentage bar diagram when this volume is in percentage. If not percentage, subdivided bar diagram can be used. Each volume of the characters are converted to percentage. Of course, this each volume of the characters converted to percentage in this percentage bar diagram. In this diagram, each attribute will have 100 as its maximum volume. Of course, we can observe for all the attributes, the bars are all are equal to 100%. Here from this type of diagram, we can have meaningful comparison and relative changes in data easily. This is better than subdivided bar diagram. Let's consider mango production from this table. Mango production in 2005-6, observations in million tons. This can be used in this type of diagram. So mango production, so different diagrams I have taken here legend. Here in this diagram, we have converted each volume into angle degrees. Angle is equal to component value divided by total of component values into 360 degrees. From this table, we can observe Chikmagalur 58,000, we converted to 58,000 divided by, so this the 1,27,500 is the total of all these things, 58,000 plus 34,000 plus 3,000 plus 32,500. The whole thing is 1,27,500 into 360 degrees. This becomes 164 degree. So 164 degrees, this one. Chikmagalur is 164 degrees. Like this, Chitradurga, the same, the volume can be converted to degrees. 96 degrees, Kodagu 8 degrees, Shumaga 92 degrees. In this way, we can have the diagram. This type of diagram is known as pi diagram. Pi diagram. Everything is converted to degrees. This pi diagram is a circle is subdivided into various sectors. Here we can observe these are the sectors. Here 4 sectors are there. The sectors are proportional to components value of the characters. Of course, this sector is proportional to component factor 58,000. This 164 degree proportional to 58,000. It is also known as pie chart or angular diagram. It is a two-dimensional diagram. Of course, we can see length and breadth is using here. This is two-dimensional diagram. To compare the volume of single characteristic between different attributes, we can use this pie diagram. Of course, we can use pie diagram instead of simple bar diagram. We can observe the same table I have used for simple bar diagram. This data can be represented through simple bar diagram also. Coming to construction of pie diagram. First thing, we have to convert for given component values, find the corresponding angles in degrees by using the following formula. Formula can be used, and the next, these angles are taken to nearest integral values. So why we have to take nearest integral values means total should be equal to 360 degrees. Using a compass, draw a circle of any convenient radius. Circle we have to form. Then using protractor, divide the circle into sectors whose angles have been calculated in step 1. Here sectors are to be in the order of given items. Of course, first, second, third, fourth, that should be in the order. Sectors should be in the order. Each sector marked or colored differently in order to distinguish them. So we can give colorings for each sector. We have to write the title for the diagram and we have to write the legend and legend to be in the order of given values. Of course, these construction steps are required for exam purpose. Now coming to graphs, types of graphs. There are 4 types: histogram, frequency polygon, frequency curve, cumulative frequency curve or ogive curve. Now, I'm considering here the plant height. This is a continuous frequency distribution. This is a plant height. This is class interval I've taken and number of plants. So 0 to 10 centimeter, there are 3 plants. 10 to 20 centimeter, 4 plants. 20 to 30 centimeter, 8 plants. 30 to 40 centimeter, 5 plants. So total, these are 3 plus 4 plus 8. Total 15 plants are there. Total 3 plus 7, 7 plus 8 is 15, 15 plus 20 plants are there. So this is a distribution table. Continuous frequency distribution, we can say. This distribution can be represented through this type of graph. So here 0 to 10, so 0 to 10, 10 to 20, 20 to 30, 30 to 40. So these are frequencies. I have taken here frequency. This is 3. For the first class interval, frequency is 3. Second class interval, frequency is 4. Third class interval, 20 to 30, frequency is 8. 30 to 40, frequency is 5. We can observe. This type of graph is known as histogram. It is a graphical representation of continuous frequency distribution where frequencies of the respective classes are represented by set of rectangles, where the frequencies of the respective classes. So frequency of the respective classes are represented by rectangles, set of rectangles. Width of rectangle is equal to respective class interval. So this width 0 to 10, this width is equal to respective class interval 0 to 10. Class interval is 10 here. Of course, in this distribution, all the classes are equal. Height of the rectangles is equal to respective frequencies. Height of the rectangle is proportional to respective frequencies. So this proportional to first class interval, this height proportional to second class interval, third proportional to 20 to 30 class interval. Area of the histogram represent total frequency. This area of the histogram represent total frequency. This is 20 is a total frequency. All the rectangles touch each other but never overlap each other. This is a property of the histogram. Touch each other but never overlap. It cannot be used to compare 2 or more frequency distribution. So this is only one distribution we can represent through this histogram. If we have one more type of distribution, another distribution, we cannot compare here itself. We have to use different graphs. It is a 2-dimensional graph. Of course, in x-axis also we have taken the values and y-axis also we have taken the values. So length and breadth are used here. Coming to this construction of this histogram, the same table, how to construct this diagram. So directly I have taken the diagram here. The procedure is there. Some steps are there. First, we have to construct x-axis and y-axis. This is x-axis and y-axis. Plot the lower limit of all the exclusive classes on the x-axis. So x-axis we have to take lower limits 0, 10, 20, 30, 0, 10, 20, 30, and also we have taken to complete the diagram as a 40 as a lower limit. The lower limit of the lowest class is taken at the intersecting point of x-axis and y-axis. Of course, 0 is the lower limit we have taken at intersecting point. Frequencies of the classes are taken on the y-axis. Of course, we have to take frequencies. This is number of plants. We have taken 0, 2, 4, 6, 8, 20. Of course, 20 total, but maximum is 8. But here we have taken 10. A separate rectangle is used to represent specific frequency of the respective classes. Separate rectangle. So previous slide I have explained the separate rectangle we have to represent for the frequency of the respective classes. width of all rectangle is equal to respective class interval. Okay. Height of rectangle is in proportion to frequency of the respective classes. Here, one more point, if the class intervals are not equal, so of course, in this table, all the class intervals are equal. Sometimes, if this last distribution is 30 to 50, last class interval is if 30 to 50, in that case, we should not use these frequencies. Instead of these frequencies, we have to use frequency density. Frequency density is equal to frequency of the class divided by width of class interval. In that case, for if this class interval is 30 to 50, in that case 5 divided by this class interval is 20. 30 to 50 means the width is 20 and this 5 divided by 20. In that way, for everything we have to convert like this, then construct histogram. This is another type of graph. Here for this table, we can represent this table in this way also instead of histogram. This type of diagram, in this type of graph is known as frequency polygon. It is a graphical representation of continuous frequency distribution where the frequencies of the respective classes are represented by dots. Of course, this dot, here dot, dot. And all the dots are joined by straight lines. So straight line we have joined. So 0 to 10, this is the frequency 3, 10 to 20, 4, 20 to 30, 8, 30 to 40, this point is 5. So at last we are joined by straight lines. This is known as frequency polygon. Frequency polygon is used to compare two or more frequency distribution. Of course, if you have the distribution like another distribution like this, in this diagram, in this graph itself, we can compare. But in histogram, it's not possible. This frequency polygon gives fair idea about the shape of the frequency distribution, whether right tail or left tail or whether it is normally distributed. We can see from this graph. Coming to construction of frequency polygon. How to construct this frequency polygon? First, construct x-axis and y-axis. Of course, this x-axis and y-axis. Plot the lower limit of all the exclusive classes on the x-axis. Of course, all the lower limit of the points here 0, 10, 20, 30, 40. Plot the lower limits. So 0, 10, 20, these are the lower limits. Here we have taken exclusive classes. Sometimes these classes will be in inclusive classes. We have to convert these inclusive to exclusive classes. So in these exclusive classes only, we can use this type of graphs. Lower limit of the lowest class is taken at the intersecting point of x-axis and y-axis. Of course, here we have to take lower limit of the lowest class. Frequencies of the classes are taken on the y-axis, of course, y-axis. The frequencies of the respective classes are plotted by dots against the midpoints of each class interval. Of course, these are the dots. So we can observe dots here. Dots. These dots can be plotted against the respective classes. Frequencies of the respective classes are plotted by dots. We can observe here dots. The midpoints of each class interval. So this is a midpoint here. This is midpoint here. This is a midpoint here. Then all the dots are joined by straight lines. These points or dots are joined by straight lines. Frequency polygon can also obtain by joining the midpoints of the tops of the rectangles in histogram by straight lines. Of course, this histogram, we can have the rectangles. For the rectangles on the top, we can mark the midpoint. Then those midpoints also can be joined. From the histogram also, we can have the frequency polygon. This is another additional feature, that's all. Coming to another type of graph, this distribution can also represent through this type of graph. This type of graph is known as frequency curve. You can see the curve here instead of straight lines. It is a graphical representation of continuous frequency distribution. So we have to see continuous frequency distribution, where the frequencies of the respective classes are represented by dots. These are the dots. All the dots are joined by smooth curve. Smooth curve, if you use smooth curve, that becomes frequency curve. If you use straight lines, that becomes frequency polygon. This frequency curve is used to compare the two or more frequency distribution. This is another property. It gives fair idea about the shape of the frequency distribution. Coming to construction of frequency curve, the same pattern of frequency polygon. Construct x-axis and y-axis, plot the lower limits of the exclusive classes on the x-axis. The lower limit of the lowest class is taken at the intersecting point. Frequencies of the classes are taken on the y-axis, of course y-axis. This is a frequency, number of plants, 0, 2, 4, 6, 8, 10. The frequencies of the classes are plotted by dots. Of course, these are the dots. So these are taken in different places, okay, against the midpoints of each class intervals. Then all the dots are joined by smooth curve. This are taken in different places. We have to join these points smooth curve. Plant height. This is another table. These tables we can observe. This is the class interval, number of plants, that's a frequency. So third column is less than cumulative frequency and last column is more than cumulative frequency. The less than cumulative frequency, in the previous video I have explained how to get less than cumulative frequency, adding these things from the top. More than cumulative frequency, adding those frequencies from the bottom, 5 plus 8 plus 4 plus 3, like this. So total frequency is 20. So we are getting here this total frequency is 20. From this table we can have the cumulative frequency curve or OGU curve. It is a graphical representation of the cumulative frequencies of continuous frequency distribution. There are two types, namely less than cumulative frequency curve or less than OGU curve. So from this first column and third column, if these first and third column can be used to construct less than cumulative frequency curve or less than OGU curve. Another type is more than cumulative frequency curve. This, of course, more than cumulative frequency curve, it can be obtained for more than cumulative frequency. Coming to less than cumulative frequency curve. Less than cumulative frequency curve. From this table, we can observe this is a class interval. Second column is less than cumulative frequency. So adding from the top, 3, 7, 15, 20. Total is 20 frequency. Total 20 plants are there. This diagram is less than cumulative frequency curve. It is a graphical representation of less than cumulative frequency distribution. Of course, these are less than cumulative frequency distribution, where the frequencies of the respective classes are represented by dots and all the dots are joined by smooth curve. Here, these are the dots. All the dots are joined by smooth curve for the cumulative frequencies, for these frequencies. It is an increasing curve sloping upwards from left to right. Of course, this is, we can observe from this curve, this is an increasing curve. It looks increasing curve sloping upwards from left to right, left to right. Coming to construction of less than cumulative frequency curve. Steps. Convert the data into exclusive type if it is given in the inclusive type. Of course, this is in exclusive, no need to convert. Obtain the less than cumulative frequency for the distribution. So for this is already in cumulative frequencies. Plot the lower limits of all the classes on the x-axis, and The lower limit of the lowest class is taken at the intersecting point. Of course, intersecting point 0 is taken here. Less than cumulative frequencies of the classes are taken on the y-axis. So here we can observe in the y-axis we have taken the less than cumulative frequencies. So 3, 7, highest is 20 here, but here I have taken 25. Not a problem. Less than cumulative frequencies are plotted by dots against the midpoints of each class center. Of course, here against the midpoint of each class center. Here taken the dot, 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 dot against the midpoints. Then dots are joined by smooth freehand curve. Smooth freehand curve. This is less than cumulative frequency curve. Coming to more than cumulative frequency, from this more than cumulative frequency, also added the frequencies from the bottom of the distribution. This is more than cumulative frequency curve or more than ogive curve. It is a graphical representation of more than cumulative frequency distribution. This is more than cumulative frequency distribution, where the frequencies of the respective classes are represented by dots and all the dots are joined by smooth curve. It is a decreasing curve sloping downwards from left to right. You can observe this is a decreasing curve sloping downwards from left to right. Coming to construction. Convert the data into exclusive type if it is given in the inclusive type. So of course this is exclusive. Obtain the more than cumulative frequency. This is a more than cumulative. Plot the lower limits of all the classes on the x-axis. The lower limit of the lowest class is taken at the intersecting point. Of course, this is intersecting point. More than cumulative frequencies of the classes are taken on the y-axis. So this is a y-axis, number of plants. Then more than cumulative frequencies are plotted by dots. Of course, these are the dots. Against the midpoint of each class, against the midpoint of each, this is in the middle, 10 to 20, the middle, we have taken the dot. Then dots are joined by smooth freehand curve. The smooth freehand curve. This is known as more than cumulative frequency. From this we can say, from this table we can have the interpretations. More than 30 centimeter, there are 5 plants. In this way, we can interpret the observation information from this table. Note, ogive curve can be used for comparative study of 2 or more distributions like frequency polygon and frequency curve. This also can be used. Cumulative frequency curve or ogive curve. Now I will brief the things, types of diagrams. This is a simple bar diagram, the multiple bar diagram or particularly double bar diagram. So we can observe the 2 bars under each attribute and legend. For the simple bar diagram, legend is not required. Why? Only single character is there. And this is subdivided bar diagram. So each bar is subdivided. The same table, some same diagram, we can have percentage bar diagram. So under each attribute can be converted to 100% for all the attributes. So here maximum is 100 for all the attributes. So legend we have to use. This is a pie diagram. The sectors, all the values converted to degrees. This is legend. Now come to types of graphs. This is a histogram, frequency polygon. So dots joined by straight lines. Here set of rectangles. Here dots or frequencies, dots are joined by freehand curve. So curve we can observe here. So this is cumulative frequency curve or ogive curve. So both the curves in the same graph. This is more than cumulative frequency curve. This one is less than cumulative frequency curve. This is a upward curve is less than, downward curve is more than cumulative frequency curve or more than ogive curve. So now I'm explaining once again the difference between diagrams and graphs. Diagrams are more suitable to represent data relating to different attributes and also variables. The graphs are more suitable to represent continuous frequency distribution and also time series data. Diagrams do not represent mathematical relationship, but graphs represent mathematical relationship. Thank you.